The properties of alcohols is going to be the topic of this lesson. And the last lesson, we're going to learn how to name alcohols. And in this one, before we move on to reactions, we're going to learn some basic physical properties, including solubility in water, boiling point, and the acidity of alcohols. Now, this lesson is part of my new organic chemistry playlist, and I'll be posting these weekly. So if you want to be notified every time I release one, subscribe to the channel and click the bell notification. All right, so let's start with the solubility in water. And so if you look at your alcohol here, again, that hydroxyl group is the hallmark here. And that hydroxyl group having an OH bond means you are capable of hydrogen bonding. And that is a big thing for alcohols. It describes a lot of their physical properties, as we'll see. So in this case, being capable of hydrogen bonding, that's a good thing if you want to be soluble in water. You might recall that the governing principle in solubility is like dissolves like. Well, what's water like? Well, water is really polar and has hydrogen bonding. Well, a small alcohol like ethanol here is really polar and has hydrogen bonding. And we'll find with ethanol, it is miscible with water. It can be mixed in any proportion. That's what miscible means here. So, but if you notice, as the carbon chain grows, the solubility in water goes down. So here we're still 73 grams per liter, which is a huge solubility, but they don't technically consider it miscible. Well, that depends on who you talk to, truth be told, but we're not going to consider it miscible here. So here you go to a 6-carbon alcohol, you're at 5.9 grams per liter, and then finally 8-carbon alcohol here with 1 octanol, and you're down to 0.3 grams per liter. And so if you look at these alcohols, the hydroxyl group is hydrophilic, but the carbon chain on the other end is hydrophobic. So molecules that have, both, portions that are both hydrophilic and then portions that are hydrophobic are often called either amphiphilic or amphipathic. So as some of these alcohols are, and the key is, water being, just all hydrogen bonding, all polarity, all hydrophilic. Water loves himself. So then the bigger your hydrophobic region, the less water is going to like you. All of these have a hydroxyl group, and water likes that part of every one of these molecules. The question is, how much does water like the carbon chain? Well, this carbon chain is the one he could deal with the most. This is the one he, prefers not to interact with the most, if you will. So, and that's kind of what's governing here the solubility in water. So the longer the carbon chain for your alcohol, the lower the solubility in water. So let's take a look at boiling points for a second. And in this case, we're not going to actually be comparing boiling points of different alcohols. I just want to show you how an alcohol compares in boiling point to some other functional groups that are similar in molecular weight and things of this sort. And you'll see that the alcohol has a significantly higher boiling point here than the corresponding aldehyde or ether. Now, I've picked, very closely related compounds that are, very similar in structure and molecular weight. And you'll see that the alcohol is highest. And again, that comes down to the hydrogen bonding, that, rather strong intermolecular force, at least compared to the other intermolecular forces. Whereas your aldehyde, it has an oxygen and it has hydrogens in various places, but it doesn't have an OH bond like the alcohol, and therefore an aldehyde as a pure liquid is not going to be capable of hydrogen bonding. It's polar, has dipole-dipole forces, but no hydrogen bonding, and therefore a lower boiling point. So with our ether here, it turns out that the carbon-oxygen double bond of the aldehyde has a little more polarity associated with it than the carbon-oxygen single bonds in the ether, and as a result, being not quite as polar, its dipole-dipole forces are even a little bit weaker. But once again, it's got an oxygen, and there are hydrogens on these carbons, but there's no hydrogens bonded to the oxygen, no hydrogen bonding, and yet again, a lower boiling point than our alcohol friend over here. So alcohols tend to have rather high boiling points than similar functional groups that are not capable of hydrogen bonding. That's kind of the point here. So next, we're going to talk about the acidity of alcohols. And the acidity of alcohol here, again, is that H that's bonded to the oxygen, not any of the H's that are bonded to carbon. So with oxygen being more electronegative, so deprotonating that oxygen is much better placed because you're going to lead to a negative charge on a more stable, more electronegative oxygen as opposed to the carbons and stuff. And so alcohols tend to be a lot more acidic than, say, just an alkane or something that's only got hydrogens bonded to carbons. So, but calling them good acids is not exactly something we'd state as far as acids go. If you look at water, water's got a pKa of 15.4, and in this case, we can see that methanol is comparable in acidity. Ethanol is very comparable in acidity, so pKa of 15.5 and 16 respectively. Now, if you look, I've kind of got a methyl alcohol. So, and then here I've got a primary alcohol, here I've got a secondary alcohol, and then here I've got a tertiary alcohol, and we definitely see a trend with our secondary alcohol here, isopropyl alcohol, pKa is 17, and then for our T-butyl alcohol, so our pKa is 19. And so we got to say, well, what's going on here? Well, if you try to explain this with our normal acid-based criteria, lose like the cardio or REO mnemonics and stuff like that, it's not really going to be very explanatory, it turns out. So it turns out there's something else coming into play here, and it turns out that is actually solubility in water of the conjugate base. And And so if you look at something like methoxide here, his conjugate base here, it's very soluble in water. But you go all the way to T-butoxide here, so, and now all of a sudden, because of this big, bulky hydrophobic carbon chain, so not so soluble in water. And so it makes it harder to deprotonate and form that conjugate base, meaning we've got a weaker acid and a higher pKa. And so general trend here is that the more substituted the alcohol, the weaker the acidity here. So, and again, rather than using the cardio or REO mnemonics, it actually is more related to the solubility of the conjugate base in water. So now we want to look at the acidity of a specific type of alcohol called a phenol. Notice that's not the same as a phenyl ring. A phenyl ring is often from a benzene ring, and that has a Y instead of an O there, but a phenol, so is our lovely aromatic alcohol here where the hydroxy group is attached to a benzene ring. And it turns out these are quite a bit more acidic than your typical alcohol. So typical alcohol in the kind of the 15, 16 range for some of the less bulky ones. So, but this guy, quite a bit more acidic with a pKa of 10. And whereas with, the trend we saw up here with regular alcohols, we couldn't explain that with the cardio or REO mnemonics, we can totally explain that here for phenols if we take a look at that conjugate base. And so if we donate that H plus right there, we end up with a conjugate base called the phenoxide ion. So I moved all my double bonds around. I'm going to try and be consistent here. So there's our phenoxide ion. And the reason, that phenols are more acidic than your typical alcohol is that the conjugate base is more stable due to resonance. So we can draw several resonance structures here. And let's do that. This will have good value here, and definitely a place where we often expect you to know a little bit more about the acidity of phenols. So that negative charge is not only on the oxygen, it's shared on this carbon right here. So shared on this carbon right here as well, and then finally, cool, so we've got 4 resonance structures here. So that negative charge is shared on one oxygen, and then 3 different carbons here. So cool, definitely more stable conjugate base than your typical alkoxide ion, like methoxide or something like that, just due to resonance. All right, so if you notice, if you look back at this phenoxide ion, so if we kind of envision just deprotonating and we see this, and we could draw all these other resonance structures. What I want to point out, though, is that if you kind of just view this structure right here alone, you can kind of look at which carbons are sharing that negative charge, and look at them being partially negative. So it's this guy right here, partially negative, this guy right here, partially negative, and this guy right here, partially negative. Now, it turns out on a benzene ring, the carbons get special names based on where they're located relative to some functional group, like in this case, relative to the oxygen. And so it turns out the adjacent carbons are called ortho. Those are called the ortho position. So if you notice, if we label this as position number 1, these would be labeled as position 2. They're 1 away. So it's not like numbering it to name it, like where I want to number all the way around, but just how far away am I from that carbon number 1 of the functional group? Well, these would be the 2 positions. They're also called ortho positions. So the 3 positions are called the meta positions, and then the 4 position relative to that functional group is called the para position. So I bring these up. We'll visit these again in the aromatic chapter later on in this semester. But I bring these up because they're pretty commonly used when we're talking about phenols. And so we've got the ortho, meta, and para positions. And if you look, so we've got resonance structures that show the negative charge being shared on a couple of on both ortho positions, and then on the one para position as well. But the meta position never shares the negative charge by resonance. It's just the ortho and para positions. And so in a minute here, we're going to look at some different groups we can attach to our phenol and how they actually impact the acidity. And what's going to be important is remembering that the negative charge is shared for that conjugate base, the phenoxide ion, on the ortho and para carbons, but not on the meta. We'll find out then different groups that can alter the acidity are going to have the biggest impacts on the ortho and para, less of an impact on the meta, as we're about to see. All right, so we're going to dive in and take a deeper look at the acidity of phenols here. And I've got phenol here, and I've got its conjugate base, the phenoxide ion here as well. And then right on your study guide here is this list of what I'm calling electron donating groups in blue and electron withdrawing groups in red. And in this case, the way this kind of table is structured is that the donating groups get more strongly electron donating as you move to the left, and the electron withdrawing groups get more strongly electron withdrawing as you move to the right. So, and these words, electron donating, electron withdrawing, are fairly descriptive. Now, electron withdrawing is a principle you're already familiar with. And it's like having an electronegative atom nearby. And we learned with the cardio or RDO mnemonics that dipole induction, or simply induction, was a way to stabilize a conjugate base, just having an electronegative helper atom nearby. Well, with a conjugated system here, there's a little more to it than just, is there an electronegative atom nearby? It turns out some groups, like the halogens, will still pull electrons away, helping to stabilize a conjugate base, and by the inductive effect, make a conjugate base weaker and the corresponding conjugate acid stronger. And so if you put one of these halogens somewhere on the ring here, then they'll be obviously on the ring in the conjugate base here, and they'll stabilize that conjugate base. And by stabilizing that conjugate base, they make it a weaker conjugate base. And if you got a weaker conjugate base, you've got a stronger conjugate acid here. So it turns out these electron withdrawing groups, not just the halogens, but all of these over here. So if you attach them anywhere on the ring here, they're going to make this conjugate base more stable by spreading the electrons out inductively, or in some cases through resonance, as we'll see. So, and if you make the conjugate base more stable, you're going to make the conjugate acid phenol stronger. So more stable base, weaker base, stronger conjugate acid. And so it turns out these electron withdrawing groups are all going to increase the acidity on your phenol. Now, it turns out where they're located is important. And as we learned before, we said that it's on the ortho positions and on the para position that shares the negative charge due to resonance. And I'm not going to draw those resonance structures out. I don't want to cloud the water too much here. But it turns out then that these electron withdrawing groups are going to have the biggest impact if they're attached in the ortho or para positions due to resonance considerations here. And so this is unique. Now, usually it would be like, well, the closer they are to the base, the more of an impact they're going to have inductively. So, and we'd say, yeah, they should have the biggest impact when they're closest to the oxygen. So here in the ortho positions, and then second in the meta, and then third in the para. That's what we'd normally think. So, but again, we saw that the negative charge is actually not just only on the oxygen, it's also shared in the ortho and para positions. And so as a result, due to resonance, the single greatest impact you can have is attaching something in either the ortho or para positions. And since the ortho is closer to the oxygen, where most of the negative charge is, because it's the major resonance contributor, so then it turns out the ortho will have precedence or higher priority, bigger impact than the para. But both of them are going to have a higher impact than the meta. And so the order here is that single biggest impact is the ortho, then the para, then the meta. And so in this case, if I wanted to put a fluorine on this molecule somewhere, if I wanted to stabilize this conjugate base the most, I'd put that fluorine on the ortho position. If I wanted to stabilize it second most, I'd put it on the para position. And if I wanted to stabilize it the least, then I'd put it on the meta position. But in every case, it would stabilize this to some degree. And by stabilizing this, you make it a weaker base, and therefore you'd make the conjugate acid a stronger acid. So these electron withdrawing groups are always going to stabilize the conjugate base, making the corresponding conjugate acid stronger. And the further you go this way in swapping out, these groups, the bigger of an impact it's going to have. So it's going to stabilize that conjugate base even more, making it an even weaker base, and therefore an even stronger conjugate acid. So in this case, if instead of a fluorine, if I put like a carbonyl attached to the ring, it'll have an even larger impact, so leading to an even weaker acid and stronger conjugate base. If I put, say, an SO3H there or a nitrile, a cyano group, even larger impact yet. And so we've kind of got this grouped into three different classes of electron withdrawing groups. The weakest electron withdrawing groups, the moderate electron withdrawing groups, and then the strong electron withdrawing groups. And you're going to kind of want to memorize them in those three classes. So you should recognize these all as being electron withdrawing. And if you look at this, it's not the worst thing in the world. If you just have an electronegative atom, well, yeah, you guys already knew those were electron withdrawing. So, but if you look at this carbonyl here, so that carbonyl carbon right there has a significant amount of partial positive charge because he's double bonded to an oxygen. That's going to, just due to the inductive, make him have a partial positive charge. Now, it turns out when he's attached to a conjugated system, he can also withdraw due to resonance, and we'll kind of see that a little bit. But at the very least, you should see that the atom directly attached has a partial positive charge. That's going to make it pull electrons out of the benzene ring here. So, and you can definitely see his electron withdrawing. If you look at all the rest of these over here that are strong ones, they are all either partially positive or full positive formal charge for the atom directly attached. So if you look at here, like in the case of NR3, that nitrogen's got a full positive charge. So same thing on the NO2 group. The NO2, it's hard to see when you just draw it out like so, but if you actually draw the functional group out, you see that the oxygen's negative over here, but the atom directly attached is the nitrogen with, again, a full positive formal charge. If you look at the carbon of the nitrile, again, being triple bonded to a nitrogen, you have a significant amount of partial positive charge on that carbon that's directly attached. So the sulfur here has a significant amount of partial positive charge being bonded to 3 oxygens. So same thing here, this carbon right here being bonded to 3 fluorines, also once again a significant amount of partial positive charge. And so we can see here a trend here, either you're a halogen or the atom directly attached is going to have a significant amount of partial positive charge based on what else it's attached to, and those are all going to be your electron withdrawing groups. Now, a little more puzzling are going to be your electron donating groups, and this is something we haven't really talked about. This is going to be new. So because we talked about, having electronegative atoms nearby, the I in REO or the DI in cardio, so totally understand that rule. But with a conjugated system, and the key is that it is a conjugated system, you might have some what are called electron donating groups. And you're at least really vaguely familiar with this kind of principle here. You just don't realize you are. So let's say we've got a carbocation here, and I've got this carbocation, and I've got this carbocation. First one here is secondary, second one is tertiary. My question for you is, if you remember, which one is more stable? And hopefully you remembered that the more substituted carbocation is more stable. And so in this case, well, why? And you might remember the reason was hyperconjugation. There's some overlap of the p orbital on this guy with some of the sp3 bonding molecular orbitals and stuff like that on the surrounding carbons. But the big thing is this. These carbons out here, through this process of hyperconjugation, are donating electron density to this carbon right here, making him less positive. It makes them all a little more positive, but it makes the central one here less positive. And if you spread out that positive charge, not through resonance in this case, but just through this process of hyperconjugation, it makes the carbocation more stable. And so by hyperconjugation, just a regular old methyl or ethyl group or whatever, so is electron donating by hyperconjugation. And so that's why the first kind of donating group is just a plain old R group, any kind of carbon chain, methyl, ethyl, propyl. So being tertiary as a carbocation is better than being secondary. That's kind of the idea. Well, in our case here, we're not talking about carbocations. I'm just using that to explain how you already kind of knew that, alkyl groups are electron donating. But it turns out if it's a benzene ring, same diff. Also going to increase the stability of a carbocation, or in some cases, we'll get back to that in a sec, but in this case, big thing is that any kind of regular old carbon chain is going to be electron donating. Now, the puzzling ones are going to be these guys right here, because you're looking, it's like, well, Chad, here it's electronegative atoms attached. Nitrogen, oxygen, nitrogen. How do we make this work? We learned that electronegative atoms are electron withdrawing, just like the halogens. Well, it's not so simple now, because now they're going to be attached to a conjugated system. And so if we take an example, like let's say we attach, say, one of these nitrogens right here. And so if there was no resonance possible involving that lone pair in the nitrogen, well, then I would agree with you. These would not be electron donating, they'd be electron withdrawing. So, like, let's just say this was just a plain old cyclohexane, not a benzene ring, and I'd agree with you. That would now be an electron withdrawing group. There's no resonance for it to take part in. This lone pair is not involved in any kind of resonance whatsoever. But the moment I put these pi electrons back into the system here, all of a sudden now these lone pairs one bond away from pi electrons, and it can participate in resonance. It can donate electrons into the ring, so doing resonance. And that's what we mean by electron donating in this case. It's electron donating by resonance. And that's much bigger impact than just simply like making a carbocation more stable by like hyperconjugation. So donating by resonance would be even better. So keep in mind, like, if we take this a little further, if I got a carbocation once again, but now I'm going to attach him to a nitrogen who's got a lone pair, now I could draw one additional resonance structure. So with a double bond there, that would put the positive charge on the nitrogen instead of the carbon, and it's an even more stable. And so this idea of resonance donating is even more of an effect than just, hyperconjugation. And so we call these the pi donors. Pi because you've got resonance with pi electrons. So, and nitrogen being less electronegative than oxygen is a stronger donating group than oxygen. Now over here, this one's kind of tricky. So here we had an amine, here we have an amide. And so we want to consider he could donate towards a benzene ring that's likely over here in the examples we're looking at with phenols. But in this case also, he could also donate over here towards the carbonyl group. And so for an amide, it's not as donating towards our benzene ring because it can also donate the opposite direction. And as a result, it's not as available to donate only to the benzene ring like these guys are. And so this is going to have an even smaller impact than even a regular oxygen like we see here, and definitely smaller than a regular nitrogen that's not part of an amide. So here in this case with this ranking here, the amine is the strongest of the donors, then an ether, and then finally down here the nitrogen of an amide, so even less so. But I like to say that your donating groups are typically a nitrogen or an oxygen that has a lone pair of electrons, or just like an alkyl or aryl group we say. Everything else ends up being a withdrawing group. And you've definitely got to know where these fall in this class. So we got the weak donors, we've got the strong donors, we've got the weak withdrawers, the moderate withdrawers, and the strong withdrawers. And once again, a lot of students get confused over here. They're like, okay, Chad, you told me that nitrogens are donating groups. Well, nitrogens, when they have a lone pair of electrons to donate, when they're attached to conjugated systems, are donating groups. But nitrogens that are full positive formal charge and don't have a lone pair of electrons, those are not donating groups. Those are actually very strong withdrawing groups instead. So be careful. All right. So in contrast to what we learned about electron withdrawing groups, how if I put an electron withdrawing group on my benzene, it's going to stabilize the conjugate base. Well, if I put one of these electron donating groups on there, it actually is going to destabilize the conjugate base. So the fact that I've attached this NR2 group actually just made this conjugate base less stable. And so if I attach it also on the corresponding conjugate acid, obviously, so by making the conjugate base less stable, that's a stronger conjugate base, and a stronger conjugate base comes from now a weaker conjugate acid. And so the withdrawing groups increase the acidity of a phenol, but the donating groups decrease the acidity of a phenol. So that's kind of the deal here. And then also, once again, if you want to influence, change the acidity of my phenol, the biggest impact you can have is if you put it on the ortho position. And so if you add one of these withdrawing groups, you increase the acidity the most by putting on the ortho position. But if you attach one of these donating groups, you decrease the acidity the most by putting it in the ortho position. So that's kind of how that works. All right, so let's make some comparisons of the examples on your handout there. All right, so the 4 phenols on your study guide are these 4 right here. And the way you want to approach ranking these as acids is you want to first identify the substituents that are attached to each and identify them either as electron donating or electron withdrawing. So if we take a look here, this NH2 group, again, a nitrogen with a lone pair attached to the benzene ring, that is an example of your electron donating group. So I'm going to label him with a D. We'll move on to CF3, and I can see that carbon, he's bonded to 3 fluorines. He's going to have a significant amount of partial positive charge. Definitely one of your strong electron withdrawing groups. So I'll label him with a W. So same thing over on this one. Also, same electron withdrawing group we had on this one. And then finally, your OME. And your OME is an example of just an OR group, where you've got an oxygen with lone pairs directly attached to your ring. And so that also is going to be a strong donating group. And once again, you should know that with nitrogen being less electronegative, he's going to be more willing to donate, if you will. And so he's a stronger donating group than him. And obviously these are the same exact withdrawing group. So if we look at how these affect acidity, so these withdrawing groups are going to stabilize the conjugate base, making the conjugate base weaker, which makes these guys as acids stronger. So withdrawing groups always make acids stronger. So both of these are going to be stronger acids than plain old phenol. But donating groups do the exact opposite. They destabilize the conjugate base, making it a stronger conjugate base, meaning these are weaker acids. And so as a result, these should be positions 1 and 2, if we're ranking acids, 1 and 2, the strongest acids, and these should be 3 and 4, the weakest acids. And let's kind of work out how this works. So in this case, we've got an example where we're comparing exactly the same substituent attached to phenol, just the location. And remember, the biggest impact you have is ortho. Well, neither one's ortho. Then para right there, and then meta right there. So both of these are stronger acids than plain old phenol, but the one with it para is going to be even stronger than the one with it meta. And so if we're ranking these, this guy's going to be the strongest acid, number 1. This guy's going to be second, number 2. Now our donating groups, they make these weaker acids than plain old phenol. And again, they're both in the same position now. They're both ortho, so they're in position to have the greatest impact on the acidity. And greatest impact doesn't necessarily mean greatest increase in acidity, because these are decreasing acidity, but they're in the position where they can have the greatest, therefore, decrease in the acidity, being that they're donating groups. And in this case, you're just supposed to know that the nitrogen is going to be a stronger donating group than the oxygen. And so this one's decrease in acidity is even more severe or significant than this one's decrease in acidity. And so this one experiencing the largest decrease in acidity will be the weakest acid, and that leaves this guy to be third. And so if you're ranking these, we got strongest acid, second, third, and then weakest acid. And that's your approach to ranking phenols. Again, label your donating withdrawing groups, kind of have an idea of where they lie in relative strength, and then also your biggest impact, whether it be biggest increase or decrease at the ortho position, then para, then meta. So now we talked about the acidity of alcohols and phenols in general. So from a synthesis perspective, you might also want to know how to deprotonate either. So this is still in the realm of acidity, but it's also part of organic synthesis. So by deprotonating an alcohol, you form an alkoxide. By deprotonating a phenol, you form a phenoxide. And the reason you might want to do that is that once you put a negative charge on that oxygen, you now have a strong nucleophile and a strong base, whereas an alcohol, he's a weak nucleophile and a weak base. So if you're trying to do like SN2, you're going to have to convert him into his corresponding conjugate base, the alkoxide ion, first. And so these are helpful reactions from a synthesis perspective. And if you look, we'll start with the phenol. And again, the phenol, much stronger acid with a pKa of 10 than a regular alcohol's pKa is in like the 16 range. And so in this case, with a pKa of 10, you can use your favorite Gen Chem strong base of NaOH to deprotonate a phenol. And notice hydroxide just going to come and take that H, and you're going to form some water. So if we draw that in, so, and if you recall, water's pKa, we said was 15.4, whereas our phenol had a pKa of roughly 10. And so we can see here that the water's a much weaker acid, and the equilibrium is definitely going to lie far to the right, which is why sodium hydroxide works. But sodium hydroxide is not going to be sufficient over here, because as our alcohol, having a pKa of 16 is not too less acidic than our water, which would be a pKa of 15.4. And so as a result, you're not going to get a good yield of this. It's not going to have an equilibrium that lies very far to the right. And so instead, we need to use an even stronger base than NaOH. And there's a couple that you might use. So we might use sodium hydride. So and sodium hydride has Na plus and H minus, and the H minus ion comes as an acts as a base. It's a really strong base, and deprotonates. And when H minus attacks H plus, it forms H2 gas and bubbles out of the solution. And it's a nice, irreversible way to pull this off. Now, it turns out you might also do a little bit of a funky reaction. So, and use either sodium or potassium metal. And so it turns out sodium or potassium metal are going to get oxidized in the process. When you're adding them, then there's zero oxidation states, and they're going to lose an electron to form either Na plus or K plus. And when they lose their electron, it's the hydrogen that gains the electron. So here, hydrogen's in the +1 oxidation state. When it gains the electron, it goes into the 0 state, and two of these are going to combine to form H2 gas, and it bubbles out of the solution, making this once again irreversible. So any of these three are commonly used. So usually the professor is going to favor one of these over the others, and sodium hydride and sodium are by far probably the most common, and sodium probably the most common, but you might see it any one of these three being the reagent of choice to deprotonate a regular alcohol. And once again, for phenol, sodium hydroxide. You don't need one of these crazy strong bases. Would they work? Well, yeah, they would, but you're typically going to use sodium hydroxide. And if you were in the lab, you would definitely use sodium hydroxide rather than using one of these crazy strong bases instead. If you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to help support the channel. If you've got questions on this lesson, feel free to leave them in the comment section below. If you're looking for the study guides that go with this lesson, if you're looking for practice problems for this, check out my premium course on chadsprep.com.